Today we are learning about linear programming. You start learning about graphing systems of inequalities in Algebra 1, but you are never told why you're learning how to solve a system of inequalities. So you finally get to PreCalculus and you learn that the application of the systems of inequalities are in economics. The name of that application is optimization. So usually if you're a businessman, you are concerned about two things, which are maximizing your profits and minimizing your costs. And you can do that using linear programming. So in linear programming, what do we have? We have an objective function. Your objective function looks like z is equal to ax plus by. That objective might be minimizing your cost, maximizing your profits, or maximizing the way in which you use the machines that you have available for your store. So you have the objective function, then there are constraints. The constraints are a system of inequalities. How do constraints arise? Well, the constraints are based on the amount of money you have available, the amount of machines you have available, the amount of people that you have working, and so on. The capacity of your machines, how many units they can produce. Next, we have feasible solutions. We'll talk about feasible solutions more as you do example 1. The feasible solutions are actually the solutions of this system of inequality. Okay, so there's a theorem that we will not prove, but that theorem says that the optimal solution of a linear programming problem occurs at one of the vertices of the region where the feasible solutions are located. So the optimal solution doesn't have to be unique. In other words, it can occur at more than one vertex. But when you get that maximum or that minimum, that maximum or minimum will be a unique number. So even though it might occur at more than one vertex, the solution will be unique. Okay, let's see. Next, we're going to look for the guidelines for solving a linear programming problem. The guidelines are on the top of page 553, right here. And there they are. The first thing that you want to do is sketch the region that is given to you by your constraints. Find the vertices of the region and then evaluate your objective function at all the vertices. The highest value will be the maximum and the lowest value will be the minimum. And that's pretty much what you need to do to solve a linear programming problem. Let's also look at the optimal solution. It is at the bottom of the page. If you read very carefully, you are told in a linear programming problem, although there are an infinite number of solutions, the maximum or the minimum occur at one of the vertices of the region. We're now going to look at the first example, at example 1. Example 1 has been written for you on the board. We are asked to find the maximum value. We are given the objective function, so this is the objective function. Objective function is given to you, and the constraints are also given to you. Those are the constraints. We start by graphing x is greater than or equal to 0, y is greater than or equal to 0. Hopefully you remember this is just the first, those are the points in the first quadrant, including the positive y and x So far, we know that our graph, our region will be in the first quadrant. So x is greater than or equal to 0. All the points to the right of the y-axis. Y is greater than or equal to 0 are all the points on the x-axis and above the x-axis. Here we go. So we're in the first quadrant. Next, we have x plus 2y is less than or equal to 4. X plus 2y is less than or equal to 4. We will subtract x from both sides. 2y is less than or equal to 4. The opposite of x plus 4. We will now divide by 2 on both sides. And we have y is less than or equal to negative 1/2 x plus 2. Our slope is negative 1/2. Our y-intercept is 0, 2. We now graph. We go 2 up on the y-axis. So 1, 2. We plot our point. Then the slope is negative 1/2. We go 1 down and 2 units to the right. Then we go another unit down and 2 units to the right. Using those 3 points, we graph a segment and then we just shade below this segment. Next, we look at the last inequality. X minus y is less than or equal to 1. So let's go over here and solve it. X minus y is less than or equal to 1. I will subtract x from both sides. The opposite of y is less than or equal to the opposite of x plus 1. Divide everything by negative 1. Or multiply on both sides by negative 1, same result. Don't forget to actually switch the sign. We have y is greater than or equal to 1 over 1x plus negative 1. The slope is 1 over 1. The y-intercept is 0, negative 1. The graph start at negative 1, go 1 unit up and 1 over, go 1 unit up and 1 over. Only draw the graph starting at 1, 0 at the x-intercept and then shade above. And now, if you look very carefully, the region is above the x-axis, to the right of the y-axis, below the blue line, above the red line. So the region that we're talking about is right here. Your region is actually a quadrilateral. We have the vertices of the region. They are 0, 2, 0, 0, 1, 0, and 2 and 1. So remember we said we were going to talk about feasible solutions. Feasible solutions are all the points in this quadrilateral that we form using the constraints system of inequalities. Like I said, even though there's an infinite number of feasible solutions, what are we interested in? We're interested in finding the maximum. Where does the maximum occur? Well, lucky for us, we don't have to test an infinite number of solutions. We only have to test 4 points, the vertices of the region. So let's do so. We have the objective function z is equal to Let's start with the point 0, 0. Clearly, we should not expect the maximum to occur there. So 0, 0 is the first point we check. Z is equal to 3 times 0 plus 2 times 0. It is equal to 0. Next, we check 1, 0. 1, comma, 0. Z is equal to 3 times 1 plus 2 times 0. It is equal to 3. Next, we check 2, comma, 1. Z is equal to 3 times 2 plus 2 times 1. This is equal to 8. And finally, we check Z is equal to 3 times 0 plus 2 times 2. I'm checking the y-intercept. I forgot to mention that. And so we get Z is equal to 4. It is clear that the maximum is 8 and it occurs at 2, comma 1. And that's pretty much it. That's how you find the maximum for your objective function. If we're asked to find the minimum will occur at the origin. There's just a little bit more. This is not a proof. So this, by no means, it's a proof. But let's take our objective function. The objective function is Z is equal to 3x plus 2y. Imagine that we subtract 3x from both sides. So you have 2y is equal to negative 3x plus z, and then divide everything by 2. Y is equal to negative 3 over 2x plus z over 2. So what is this? This is a line. The slope of this line is negative 3/2. The y-intercept is 0, comma, z over 2. How many such lines are there? Well, there's an infinite number of lines that intersect our feasible region, the region containing our feasible solutions, but we're looking for the maximum, and so we're looking for the line that has the highest y-intercept. The authors of the book, this is not a proof, drew many such lines, and we notice the darkest one right here, the one that passes through 2, 1, has the highest value of z. Z equals 8. So like I said, this is not a proof, but it is as good as a proof in this case. That's the end of example 1.